Hi everyone. Since this material comes early enough in the course that not everyone has seen differential and integral calculus yet, I thought I would make this little optional video if people who have taken calculus want to see where these equations come from. So the idea is that most of everything we've done in this chapter could be summarized in just two equations. The first one is that the instantaneous velocity as a function of time is nothing more than the derivative of position as a function of time. Velocity is the slope of position, how much the position is changing over some period of time. When you do that over very, very tiny time intervals, you get the derivative. Similarly, the acceleration tells us how the velocity is changing as a function of time. These again connect to if we had, say, a position velocity plot, or position time plot rather. We have position. We were curious of the velocity at, say, some point. We could draw triangles increasingly smaller around that point and calculate the slope of that triangle. And as we refined our triangle to smaller and smaller increments of time, some delta t, here are some delta x, that answer would converge to the derivative at a particular position. These are general equations. They are always true. In class, we did special cases where the acceleration was constant. If you want a more general set of equations, these two equations will give you anything no matter what kind of acceleration or velocity or position you throw at them. There are no assumptions that go into these equations. Now, if we want to connect them and actually find, say, given v as a function of time, what is position as a function of time, or given acceleration as a function of time, what is velocity as a function of time, or what is position as a function of time, given the acceleration. In these cases, we need to do a little calculus. So let's look at the position one first and just remind ourselves what the integral is again. So if I take this expression, I think you can all agree that this is the same thing as this. I just moved the delta t to the other side. And we can interpret this expression as you have on the left-hand side dx, which is just a tiny change in position. A very small displacement. And that displacement took place over a small change in time. And the total distance that changed during that period is the velocity multiplied by a very small change in time. And last time in class, we connected this, where if we had velocity, we had time, and we had some curve. What this represents is if I take a small little rectangle where across that rectangle the velocity is essentially constant. The velocity is not changing over that small interval. So the height of this rectangle is v in this case, which is this guy right here. And it's taking place over a very small amount of time. Looks terrible. dt. notice that the area of this rectangle is simply the height of the rectangle times the width of the rectangle. And that's all that this is representing here. The area under that curve, the velocity of that particle over a very small amount of time, gives you the change in position over that same very small amount of time. So in going from, if this was, t equals 3 seconds, and on the other side of the rectangle is t equals 3.00001 seconds. Over that small amount of time, this would tell you how much the position changed. Now obviously, we are usually more curious on what's happening over more than just, say, a microsecond. We want to know over, say, 10 seconds or a longer period of time how much the position has changed. And we talked about last time, the idea is that you can just do this process over and over again, breaking this curve into a bunch of tiny rectangles, doing the same process for every single rectangle, and then add them all up to get the total change in position. Well, I'd rather not do this for a ton of rectangles. Calculus offers us a solution. So this is the same as the mathematical integral of the previous expression. So what this means is the total change in position. More or less, you're adding up all those tiny changes and you're getting the total change overall. And then this guy is telling you exactly how the position is changing. So this is the sum of all those tiny changes, which the right-hand side actually takes into account the velocity of the object at all those very small given times. Integrals are just a fancy word for sum, or add them all up. Okay. With that in mind, and then similarly, I guess before I go on, you can do the same thing between acceleration and velocity. If dv dt, the derivative of velocity, is the same thing as acceleration, that's the same thing as saying the change in velocity is the acceleration times some amount of time. A small change in velocity is equal to the acceleration at that point times the small amount of time that passed. Again, if I want the total change in velocity, I add up all of those small changes, and this gives me the total change in velocity. And that's calculated again by taking into account the acceleration and how much time is passing between the start and finish point. With calculus, this is more straightforward. Let's go then. So let's try first to just rederive the equations that we saw in class. So those were the case where we made the approximation or assumption that let the acceleration be a constant. So in that case, if v equals v0, or some initial velocity at t equals 0, and the position of the particle is some initial position at t equals 0. What is the final velocity and the final position at some later time, which I'll say is t sub f? All right. So in this case, we are treating the acceleration as constant, which will make it easier when we actually do the integrals. So again, start general. dv dt equals a, which in this case is a constant. This is always true, except for the assumption that the acceleration is constant in this case. That can be rearranged to say dv is this constant acceleration times time. We will now integrate this expression, but we can be, more precise about this compared to what we did before. On the left-hand side, the variable that we're integrating over is the velocity. So the limits of integration in this case is going to start at our initial velocity and end at our final velocity. On the right-hand side, what we are integrating over is time. So our limits of integration are the initial time, which in this case we're going to call 0, and our final time. And this, we can do each of these independently. So the integral of dv from the initial velocity to the final velocity, this is just the integral of a constant, is just the variable itself over the limits of integration. So this is just the final velocity minus the original velocity. Similarly, for the right-hand side, the integral from 0 to the final time of the constant acceleration over time, the area under our curve where the curve has 0 slope and it's just the constant value of a naught, is just a naught times t, evaluated between the final time and the original time, and that is just a naught t final. Putting everything together, the left-hand side was v final minus v naught. The right-hand side was a naught times t final. If I rearrange this and drop the f's and just say as v equals v naught plus a naught times t, which is the expression we had in class. Given that, we now ask ourselves about position. So the derivative of position is just the velocity. This is a general result. So the change in position is the velocity times the change in time. Again, integrating, we have to supply our limits of integration. The left-hand side, we're integrating our position. So this is going from our initial position to our final position. The right-hand side, we're integrating over time. So our limits of integration are our initial time and then our final time. We can go a step further because we know the velocity because we just calculated it. The velocity in this case is the initial velocity times a naught times t, all integrated over time. The left-hand side is pretty straightforward. Just that. kind of similar to what we saw previously with velocity. This guy, if you integrate, you have a constant term, and then you have the term with acceleration, and since there's a t, you use the power rule for integrals, so that becomes t squared divided by 2. This is all evaluated between 0 and the final time. So this just becomes the initial velocity times the final time plus 1/2 the acceleration times the final time squared. Putting everything together, the left-hand side is the change in position. The right-hand side is the expression we just drove. If I rewrite it, but drop the f's, then I simply get which is the expression we got in class. To me, it's a little more straightforward viewing it through calculus, because you're really just looking at the incremental changes in velocity, taking into account the constant acceleration, and then once you have how the velocity is a function of time, you know exactly how it's changing when you calculate the area under the curve for velocity, and that gives you position, which are the two expressions in the boxes. So let's see, I think that deserves a smiley face. That aside, while the equations for constant acceleration are ones we will do in class, you might be curious, and there are problems in your book you might be curious to solve of, if I say, if the acceleration as a function of time is some function of time, I'm going to be sloppy and not deal with units right now, so forgive me. So if the acceleration is, say, 3 times the square of time in some arbitrary units, and the velocity initially is 0, so the particle starts at rest, and the position initially is 0. It starts at the origin. Remember, this is t equals 0, and this is, the origin, and this is it's starting at rest. One could ask, what is v in general, or the position in general at some later time greater than 0? Now, you would not use the equations we boxed on the previous page, because those make the assumption that the acceleration is constant. In this case, the acceleration is not constant. Particularly, it increases with time. As time gets bigger, the expression here gets larger. But that doesn't stop us. Going back, we have this expression, which is always true. If I want to know velocity, I can always integrate it. I'm starting from my initial velocity, which we said is 0, and going to some final velocity. We'll call it v sub f again. On the right-hand side, I'm integrating over time. We're starting at 0 and going to some later time. But I know the acceleration is 3t squared dt. So I can do this integral. This guy here is again just v final minus v initial, which in this case is just 0. This guy here is 3t cubed divided by 3, using the power rules for integrals, evaluated between the final time and the initial time, which is just 0. You can see this is just the final time cubed. Putting it all together, this just says the final time, or the final velocity rather, is some expression that has time cubed. And again, forgive me that I'm not being careful with units, but there would be some constant out here that has a value of 1 but has units in it that makes this all work out. If I drop the subscripts, you might say v as a function of time in this case is just t cubed. Then you want to finish. You want to do the position as a function of time. Position is the left-hand side. The limits are the initial position, which we set as 0, to some final time. The right-hand one is integrating over time again, so again from 0 to t sub f. The velocity we just calculated is t cubed. And again, using the power rules, that becomes t to the 4th over 4, or just the 4th power of the final time divided by 4. This guy, again, is just the final time minus the initial, or the final position minus the initial position, which is a 0. Putting it all together, it just says the final position is, ignoring units, t to the 4 over 4. If I drop the subscripts, the function is just t to the 4 over 4. So again, in the most generalized form, if I go back to this guy, anything that's thrown at you can be solved with these guys. If it is, the assumption is made that the acceleration is constant, then these are the expressions for the velocity and the position. If the acceleration is not constant, like in this case, then you actually have to redo the integrals again. Don't just use the formulas on the second page, and derive it for yourself for that very specific acceleration. Once again,